Okay, we're in the last video, number 6 for the chapter. We're looking at chapter 9, quantities calculated in chemical reactions, so calculations from balanced chemical equations. And we just talked about theoretical yields. If you're given the quantity of 2 reagents, how do you know how much product you make? Well, you calculate the amount of product from each reagent amount given. The one that gives the least amount of product was your limiting reagent, and that determines how much product you're going to make, because it will be consumed or run out when the reaction is completed. So the amount of product you can make in a chemical reaction, we said from the limiting reagent, was called the theoretical yield. The quantity of product that could be obtained should the reaction go to completion. And we said that was calculated using the quantity of the limiting reagent given, the one in less amount stoichiometrically. All right. Notice what theoretical yield says. It's the quantity of product that could be obtained should the reaction go to completion. One thing we've been assuming this entire chapter is that if you put 2 reactants together, they're going to completely react stoichiometrically, and you're always going to get 100% of your product out. Or the reaction will go all to completion, which means you'll have product and no reactant left, unless you have excess. That's not always the case. In the real world, not all reactions go to completion. Sometimes reagents aren't completely pure. There's solvent effects, incomplete collisions. There's all these things, but most of the time, whenever a chemical reaction occurs or you're synthesizing a product, there's always a little bit of reactant left. It seems almost impossible to get a completely pure product with nothing else left in that reaction mixture in the real world. So how much product you actually make versus how much on paper you should make are never going to be the same. If your theoretical yield on paper was 50 grams, your actual yield is going to be a little bit lower than that. It's either equal to, but not usually, or a little bit less than the theoretical yield. So let's say that you calculate on paper with all your limiting reagents and everything that you're going to make 50 grams of product. On paper, that's your theoretical yield. When you go to actually run the reaction in the lab, you might get 40 grams of product instead of 50. So the actual amount that you recover in the lab is your actual yield. It's usually equal to or lower than your theoretical yield. Okay. What do chemists do when they get a difference in actual versus theoretical yield? It turns out that usually, not always, but usually that yield that they get is reproducible. So what they do is they give an overall efficiency of the reaction. They calculate something called the percent yield. And the percent yield is calculated by dividing the actual yield by the theoretical and then multiplying times 100. So I'm going to give you, let's erase that. I'm going to give you the equation for percent yield here. Percent yield is the actual yield, usually given in grams, divided by the theoretical yield that's a ratio, times 100%. Now, when you calculate a percent yield, you're going to get a ratio of actual to theoretical. Remember that the actual yield is usually equal to or less than the theoretical yield. Let's say that your actual yield is the same as your theoretical yield. For instance, you made 50 grams in the lab and you calculated that you should make 50 grams on paper. 50 over 50 equals what? 1. Multiply that times 100 and you would get an efficiency of 100% yield, which means that every time the reaction went, 100% of your reactant would be converted to product. That's what the percent yield means. Notice, though, that the actual yield can either be equal to or less than. If we made, for instance, 40 grams of our product, but on paper we were supposed to make 50, this would be an example of a ratio where the actual yield was less than the theoretical. 40 divided by 50, that's 4/5. Multiply it times 100. that would be 80%. Your yield would be 80%. That would be lower than efficiency. What does that mean, that percent yield? 80% of your reactants would be converted to products. That's what that means. So percent yields are usually 100% or less than 100%. Why can they not be more? They can never be more than 100% because you cannot make more yield than you theoretically can make. The maximum yield you can make is called your theoretical yield. The actual yield is usually lower. So your efficiency is either 100% or less, your percent yield. So let's look at some examples of how we could calculate percent yields if we were given some information from a chemical reaction. Okay, here's an example. It says, in a reaction to produce ammonia, the theoretical yield is 420 grams. What is the percent yield? So we don't know what the percent yield is if our actual yield is 350 grams. All right, this is a really easy one, I'm not going to lie. You just take the equation you're given and you plug in the values, right? So what is the percent yield? That's exactly what we're going to be solving for. Percent yield is always actual yield divided by theoretical yield times 100. All right, so you're given that equation, know how to use it. Okay, we're given numbers here. It says the theoretical yield is 420 grams. The actual yield was 350 grams. So 350 divided by 420 times 100. All right, let's get our calculator out. I've got 350 divided by 420 equals, I've got 0.83333 repeating, times 100. Okay, 83.33333 repeating percent. Well, notice I've got three significant figures on top, on bottom. I'm dividing. My answer is going to have three significant figures. So I'm going to have 83.3% as my yield. 83.3% is the percent yield of this reaction. All right, let's try one that's a little more difficult, shall we? All right. Erase this and get it out of my way. Let's see here. So the next problem says calculate the percent yield. So we still want to calculate the percent yield again of PCl3. Accidentally wrote on top of that. Let's just go ahead and write the percent yield equation. Whenever I know I have to calculate something and it is an equation, I always start by writing the equation down and figuring out if those pieces are given. So percent yield is going to be actual yield divided by theoretical, and I'm lazy so I'm not writing everything. Actual divided by theoretical times 100%. So I'm going to need, oops, I don't know why I wrote grams there. I get excited. All right, so percent yield is actual yield divided by theoretical yield times 100. So if I'm going to calculate a percent yield, the reason I wrote that down is I'm going to need the actual yield, how much was actually made. And I'm going to need the theoretical yield, how much could have been made if all of the reaction went to completion. All right, let's actually read the whole problem now, right? Okay, it says calculate the percent yield of PCl3, my product here. So there's my product. The results from reacting 5 grams of phosphorus. So now I'm given some numbers. 5.00 grams of phosphorus. It says with excess chlorine. Remember when it says excess, that means don't worry about it. It's the excess reagent. If only 17.2 grams of the phosphorus trichloride were recovered. What does that mean if 17.2 grams were recovered? That's my actual yield. That means in the lab, somebody ran this and they only recovered 17.2 grams. That's my actual yield. Okay. So I'm going to rewrite this, and I've got 17.2 grams as my actual. Do I have my theoretical yet? Let's go back and read. Okay, so I need my theoretical yield here. Let's find it. It says calculate the percent yield, so we still have to find the percent yield. That's our question mark, okay, of phosphorus trichloride that results from reacting 5 grams of phosphorus. Well, that's my reactant. That is not my theoretical yield of my product. So that's not it. With excess chlorine, if only 17... Okay, I don't have any other numbers here, do I? I have the 5 grams of phosphorus, but that's my reactant. I want to know what the theoretical yield of the product is. How do I come up with the theoretical yield of product? Well, I know how much reagent I'm given. I'm given 5 grams of phosphorus. The theoretical yield says if you take your limiting reagent, since we know chlorine's in excess, if all of that is consumed or all of that reacts, you can produce your theoretical yield in grams. So I want to know how many grams of phosphorus trichloride could be produced. So really that's my question. How many grams of phosphorus trichloride are produced? Well, we're given grams of phosphorus. Let's convert it to grams of phosphorus trichloride. Okay, let's set up a solution map. So here I'm given grams of phosphorus. That's what I'm given. I need to figure out grams of phosphorus trichloride, right? Can I convert grams of one reagent straight to grams of another reagent? No! What's the central unit in this chapter? In this whole unit? The mole. I've got to go through the mole. So I can convert moles of phosphorus to moles of phosphorus trichloride. Okay? I can do that using my mole ratio. Okay. But I'm not given moles of phosphorus, and I'm not asked for moles of phosphorus trichloride. I need my grams of my phosphorus trichloride for my theoretical yield. But can I convert in and out of the mole? Why, sure I can. I can convert grams of phosphorus to moles of phosphorus. And from moles of phosphorus to moles of phosphorus trichloride. And then once I figure out my moles of phosphorus trichloride, I can convert, to grams of phosphorus trichloride. I can convert grams to moles using molar mass, and I can convert from moles back to grams using molar mass. So now we need to come up with a molar mass, because this isn't given to us either in this problem. This is like a big problem for us. We need to figure out everything that we've learned in this last chapter. In this last chapter, in order to be able to solve this problem. So I'm going to need the molar mass, but it's not given. So what's the molar mass for phosphorus? We'll look on your periodic table. Phosphorus is number 15 on the periodic table. The molar mass is 30.97 grams per mole. So 30.97 grams per mole for phosphorus. What is the molar mass of phosphorus trichloride? Well, we've got 3 chlorines. Chlorine weighs 35.45. So multiply that times 3, that's your chlorine. We're going to add the phosphorus, 30.97. Is that right? Okay. Yeah. So my molar mass that I calculate for phosphorus trichloride is 137.32 grams per mole. We're going to need all of these numbers to do our calculation. So let's start with what we're given. Oh my gosh. We're given grams of phosphorus. We're given 5 grams of phosphorus. So we're going to start there. 5.00 grams of phosphorus. We're going to convert grams of phosphorus. Remember how we go into the mole? So I'm going to convert grams of phosphorus, I'll use my highlighter, into the mole. Then I'm going to do a mole to mole, and then I'm going to go out of the mole. Alright? So let's do our grams of phosphorus to moles of phosphorus. So we said that the molar mass of phosphorus was 30.97 grams for every 1 mole. Alright, so I've got my grams of phosphorus on top and bottom. Those will cancel. So I've converted into the mole. Now I need to do my mole to mole. I need to convert moles of phosphorus into moles of phosphorus trichloride. Now, notice here that for every 2 moles of phosphorus, I make 2 moles of phosphorus trichloride. Go ahead and write that in there. If you try to skip this step, your life will be a nightmare sometimes. So don't skip until you're an expert, okay? I know some of you are like, skip, why would I ever skip this? Well, if you've had classes before, you'll know sometimes people start to skip. Don't skip. Always just write it. So for every 2 moles of phosphorus, there's 2 moles of phosphorus trichloride produced. So I went from moles of phosphorus, mole up, mole down of phosphorus, to moles of phosphorus trichloride. That was converting moles to moles, moves my molar ratio. And now I'm going to do my out of the mole. So I went into the mole to mole, out of the mole. I did my IMO. Okay, so we're converting out of the mole. We said that there's 137.32 grams for every mole of phosphorus trichloride. So here we go. We've got, for every 1 mole of phosphorus trichloride, there's 137.32 grams. So I've got my moles of phosphorus trichloride on top and bottom, and they cancel. So let's figure out how many grams of phosphorus trichloride we can make from 5 grams of phosphorus. That's really what we're doing here. We've got 5 times 2 times 137.32. So equals, I've got 1,373.2 divided by, now I'm going to multiply my entire denominator in parentheses. 30.97 times 2, close parentheses. Okay, here's how many grams of phosphorus trichloride we make. From 5 grams of phosphorus, we are going to make 22.2 grams of phosphorus trichloride. Okay. Whew, I'm exhausted after that one. Okay, so what is that? That is our theoretical yield. Let's not forget what we've done so far. We said we're starting with 5 grams of phosphorus. We wanted to know on paper, if I consume all 5 grams of that phosphorus, how many grams, theoretically, of phosphorus trichloride could I make? It's getting really late, isn't it? All right, that's my theoretical yield. I'm going to plug that in my equation, because I was given the actual yield, 17.2 grams. Now do you see why it says only? When you read this question again, it says, calculate the percent yield of phosphorus trichloride, that reacts from reacting 5 grams of phosphorus with excess chlorine. Here's the part. If only 17.2 grams were recovered. You see why they said only now? Because on paper, it looks like if all of that phosphorus reacted, you should make 22.2 grams. So, let's calculate the percent yield now. The percent yield is always the actual divided by theoretical times 100. So we've got 17.2 divided by 22.2 equals, there's my ratio, multiply it times 100, you got the percent. It looks like it's going to be 3 significant figures, so I've got 77.5% yield. That's my efficiency of my reaction. For every gram of phosphorus, 77.5 grams of the phosphorus, or moles of phosphorus, react to produce product. So there's my percent yield. Now I would consider that a challenging problem. So that's a good one to stop with because it contained everything we've been doing this whole chapter. Now if you think about it, actually when you read the chapter, it's a really short chapter in the book. So I encourage you to go back if you've read it and go ahead and read it again. You will learn so much just sitting there reading the chapter and thinking over it for yourself. Don't skip the problem-solving boxes where it gives you a problem and discusses it. That's your main point in the chapter where you can really learn how to solve the problems. And then after those, do some problems on your own. Okay? Like I said, it's a very short chapter. There's only a few concepts in it. However, they can be stumbling stones for people that haven't practiced enough. So what do I always end with? I always say practice, 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 because practice makes perfect. Be comfortable enough that you can come in and you can just work through the exam quickly, do the exam, and you feel confident. All right? Okay.